All right, so I wanted to take some time to go over optimization and to work through a few examples. This is going to be a rather long video, so it's going to be indexed with where you can go for individual examples. But I'm going to do the steps, and then we're going to do 5 examples in this video, so you can sort of have them all in one place. So the steps for optimization are: you want to start by identifying the quantity to be maximized or minimized, identify the independent variable or variables upon which that quantity depends, and then write an equation relating the quantity to be maximized to the independent variables. If necessary, substitute to get this equation down to, down to one dependent and one independent variable. Step 3 is to identify the relevant domain. Step 4, optimize your function over your relevant domain. And step 5, state your solution. So those are the steps. And here's our first example. The first example: if an open rectangular box with square base is to be made from 48 square feet of material, what dimensions will result in a box with the largest possible volume? So the first thing I want to do is I want to identify the quantity to be maximized or minimized. So if you read the problem, it says what dimensions will result in a box with the largest possible volume. So this is the thing I want to maximize. I want to maximize volume. And we'll call that, since I'm trying to maximize volume, let's call that V. And then I want to identify the independent variable or variables upon which that quantity depends. Well, this is a rectangular box. I think a diagram would be helpful in this. So I'm going to draw a diagram. And my box looks like this. It says it has a square base. So the base, the length and the width are the same, but the height is something different. And we're told that there's no top on it. It's an open rectangular box. So I want to maximize the volume, and the volume of that box is going to depend on the length of these 3 sides. So the independent variables I would have would be x and h, and since I've labeled them in the diagram, that counts as sort of defining what the variables are. So dependent variable, independent variables. So now I want to write an equation relating the quantity to be maximized to the independent variables. So that's the volume of a box. Usually on this step, you're going to end up using knowledge that you have from geometry. So you know how to find the volume of a box. It's length times width times height. And it's x squared h because the length and the width are the same in this problem. Now, notice the second part. If necessary, substitute to get this equation down to one dependent and one independent variable. What I've got here is a dependent variable, volume, and 2 independent variables, this x and this h. So I need some other piece of information in the problem that will allow me to get just x or just h, not both. So what I do there is look back in the problem and look for a quantity that I've been given. Let's see, it says open rectangular box with a square base is to be made from 48 square feet of material. So that means basically when I add this surface area of all these sides together, it would give me 48 square feet. So if I think about this box, the square base would be x squared, and the 4 sides would all have an area of x times h, so there's 4 of them, so 4xh. There's no top, so there's only the one square, x squared thing. And when I put those together, that would give me 48 square feet. Now I'm going to take this, solve it for one of the variables, and h looks like the most probable one here, and substitute it into the thing that I'm trying to maximize. So this would be 48 minus x squared all over 4x. And I could simplify that up a little bit if I wanted to. I'm just going to plug it into the volume equation for h, and that will give me an equation where volume is expressed in terms of only one independent variable, which is x. Now, before I get all happy and start doing the next step by identifying the relevant domain, I'm going to go ahead and simplify this thing. So the x on the bottom would cancel out with this x on the top, and if I did a little bit of routine sort of simplification here, I would get 12x here, and I believe I would get negative 1/4 x cubed. Okay, So this is going to be the equation I'm going to take the derivative of in step 4 when I go to optimize the function. But I need a relevant domain. And the way to figure out the relevant domain is you come back to the problem, and almost always in these problems, the smallest your independent variable is going to be able to be is 0. The question is it possible? So is it possible for my x to be 0 and for me to have an area of 48? And the answer is no, because if my x was 0, this would be 0, and this would be 0. So I would not include that, comma. And then I want to talk about what would happen as the other variable, the h, gets as small as it possibly could be. So if h were to go to 0, then this term would go away, and it would leave me with x squared equals 48. So the biggest x could be is the square root of 48 here. And that's actually physically possible, so I'm going to include that. All right, so I've got my relevant domain, that's here, and I've got my equation that I'm trying to optimize, which is here. So now I'm going to take the steps. I'm going to take the derivative. That's 3/4 x squared. I would set that equal to 0 and solve. So if I set that, or I would look for where it's undefined as well, but in this case it's not undefined anywhere. So if I set that equal to 0, I'd have 12 is equal to 3/4 x squared. And if I multiply both sides by 4/3, that would give me 16 equals x squared. And x would be plus or minus 4. But the negative 4 isn't in the relevant domain, so I don't care about it. Only the positive 4 is. So now I'm ready to do the sign line for this. So I put a sign line down, put my endpoints on it, and then I'm going to put my point, in the middle. So that's 4. And I plug in numbers on either side of 4. So when I plug 1 into the derivative, that gives me 12 minus 3/4, which is positive. If I plug in like 5 into the derivative, that gives me 12 minus 75/4, which is negative. So this is going to increase and decrease. Now, you could plug in the endpoints and compare it with what you get when you plug in that 4 into the original function to sort of compare the y values. But here we have only one relative extremum. And we have that theorem that says if there's only one relative extremum in an interval, it is the absolute extremum of that type. So since this is the only relative max, it's the only relative extremum we have, and it is a relative max, that it is the absolute max. So then we've optimized our function. We know that the optimum volume happens when this x is 4. Now we need to figure out what our solution was asking. So the question said, what dimensions will result in a box with largest possible volume? So I want the dimensions. The question didn't ask for the volume, it just asked for the dimensions. So when I give my answer, I need to give the dimensions and I need to put proper units on it. So I know my x is 4 and my units would be feet, and that's the dimensions of 2 of those lengths. And then to find the third dimension, which is the height, I can go to this equation right here and plug that 4 in for x. So that will be 48 minus 16, which is what, 32 over 16, so that would be 2. So it's 4 feet by 2 feet by 2 feet. And that would be the solution to that problem. So let's move to another example. This problem says that a container in the shape of a right circular cylinder with no top has a surface area of 3 pi feet squared. What height h and base radius r will maximize the volume of the cylinder? So here we go. Identify the quantity to be maximized. Well, the problem says maximize the volume of the cylinder. So we want to maximize volume, which I'm going to call V. All right. And then identify the independent variable or variables upon which that depends. Well, this is a volume of a cylinder, and in the cylinder, if you don't remember, a lot of times this would be given to you on a test, that the volume is pi r squared h. So I'm going to write that down. So this is the thing I want to maximize. I want to maximize the volume. And I need you to find my variables. So the h in the picture is the height of the cylinder, and the r is the radius of the cylinder. So I'm going to go now to step 2, which is write an equation relating to do that. I've already just done that, kind of just done that, right? If necessary, though, substitute to get this equation down to one dependent and one independent variable. And again, I have 2 independent variables, r and h. So I need to look back in the problem for something that is a quantity that I haven't used yet. So this says surface area with no top, which I guess I should draw that in as no top, has a surface area of 3 pi feet squared. So we know that the surface area of this thing, which I've talked about this in class before, if you don't remember, the lateral surface area of a cylinder, meaning the surface area of the sides, is 2 pi RH. And then you would add the cylinder's top and bottom, but we only have a bottom here, so it's pi r squared. And we're told that that surface area is 3 pi. So I can use that then to substitute, to solve for, looks like again, h is going to be the easiest thing to solve for, and substitute that into the thing I'm trying to maximize. So I'm going to take this, I'm going to divide everything by pi to make it prettier to start with. And then I'm going to solve for h. And when I solve for h, I believe it's going to be 3 minus r squared over 2r. And that is going to get substituted in for that h there. So I get volume equals pi r squared times 3 minus r squared all over 2r. And I would simplify that before I go on. So volume equals pi, and then when I simplify that thing out, I'm going to go ahead and just distribute it and simplify it. I believe this would come out as 3 pi over 2 times r for the first term, and then for the second term, let's see, that'd be 1/2 r times pi, so I think it's pi over 2 r cubed. I think that's right. So now I'm going to do my domain, and I'm trying to figure out what r has to be between. So the smallest r could be is 0, and I look at this information to figure out if that's possible. If I let r be 0, there's no way that 0 is going to equal 3, so I don't include it. And then I would let the other thing go to 0, which in this case would be h, and see what happens to that equation. And what I get is r squared equals 3, so r is the square root of 3. That's the biggest it could be, and that is physically possible. So that's the relevant domain. So now I'm ready to optimize this same thing. So I'm going to take the derivative, which would give me 3 pi over 2 minus 3 pi over 2 r squared. Set that equal to 0, find out where it's undefined. In this case, it's not undefined, so I'm just setting it equal to 0. When I solve this, I'm going to get r squared equals 1, because I subtract the 3 pi over 2 from both sides, divide by negative 3 pi over 2. So r is plus or minus 1, but the negative 1 is not in the domain, so I'm going to leave that off. So now I'm going to make my sign line for v prime. I'm going to remember to label it this time, because I didn't label it the first time. Put my endpoints on the sign line, and then put my critical point on the sign line. And I'm going to plug in numbers to see what happens. So if I were to plug in 1/2, which is between 0 and 1, into the derivative, remember, because that's what I'm making a sign line for, I would end up getting something that's positive. And if I plugged in something bigger than 1, I would get something that's negative. So this increases, then decreases. Again, from what we talked about before, it's the only relative extremum, and it's a relative maximum, so therefore it's the absolute max. So we know the absolute max happens there. So again, now we're ready to state the solution. And it asks what height and base radius will maximize the volume of the cylinder. It doesn't ask for the volume, it asks for the height and the radius. So I want, in this case, that this r would be 1 foot, because that's the value at which it happens, and h would be what I get when I plug 1 foot into this. That would be 2 over 2, which is also 1 foot. And that would give you the maximum volume. Now, if it had asked for the volume itself, then we would have calculated that. All right, next example. I like this one because this one's more difficult. You're standing at the edge of a slow-moving river, which is 1 mile wide, and you wish to return to your campground on the opposite side of the river. You can swim at 2 miles an hour and walk at 3 miles an hour. You must first swim across the river to any point on the opposite bank. From there, walk to the campground, which is 1 mile from the point directly across the river from where you start your swim. There's a lot of information going on. What route will take the least amount of time? So again, here we go. Identify the quantity to be maximized or minimized. Well, least amount of time, right there. So we're minimizing time. So I'm going to label time as t. Now, I need a picture of this because there's a lot going on, right? So I've got this river, and I'm standing on the edge of it, and the river is 1 mile wide. Like that. And you are trying to you're standing, say, over here, and you're trying to get to your campground. This is you. And let's say your campground is here. Okay. And it says that your campground is 1 mile from the point directly across the river from where you start your swim. Okay, so we're starting our swim immediately. The problem says that. If we were to go directly across the river, that would be here. And the problem says that this is 1 mile from your camp. All right, now you are swimming part of the way and you're walking the rest of the way. And we want to minimize time. So our path is going to involve some sort of swim across the river, like this. We're going to hit the shore, and then we're going to walk the rest of the way. So the problem says what route will take the least amount of time. The thing that would dictate that is where you actually come on shore here. So what I'm going to say is let's call this distance right here x. If that's x, then the rest of this way, the way you walked here, is 1 minus x. It's that 1 mile taking away that x. And this, from what we were given in the problem, is 1 mile, right? Okay. Now, we are talking about time, and everything that we've got in this picture right now is a distance. So what I'm going to say is, first of all, recall that distance equals rate times time. Right? You learned that back in like 8th grade. So if I were trying to find time, which is what I'm trying to actually minimize, time would be distance divided by rate. Well, we've got 2 different times going on here. We've got the time swimming, and we've got the time walking. Walk time. All right, that says walk time. Now, in order to find the time for each of those things, I'm going to take the distance that I do, and I'm going to divide it by the rate I can do that thing at. So for instance, if you look at the swim, that's the hypotenuse of this right triangle right here, right? So I'd use Pythagorean theorem, and that distance is the square root of x squared plus 1. That's the distance. But if I wanted to change that into a time, I would divide that distance I swam by the rate at which I can swim. And the problem says you can swim at 2 miles an hour, like that. So if you were to do dimensional analysis, basically, that would come out as miles divided by miles per hour, which same switch flip, would give you hours overall. So the walk time would be the distance of walking, which is much easier. It's just the straight line distance here, 1 minus x, divided by the rate at which you can walk, which is 3 miles per hour. So that's the equation for total time. Now, notice in this, because of the way I sort of worked it out, that I have only one independent variable and one dependent variable now. So that substitution step I did earlier is not, the earlier two problems is not necessary here. Okay, so now we're ready to find the relevant domain. And keep in mind our independent variable here is x, and x was this distance here that we came up on shore. So if you think about it, that x can't be any less than 0. And that's possible, because if you made x 0, that would mean you swam directly across the river and then hiked the whole way across. And that's the smallest x can be. The biggest x can be is 1, because that means you took the entire trip swimming. And that's also possible. So we're looking for a relevant domain of 0 to 1. So now we're ready to optimize this puppy. So I'm going to take the derivative of this. And when I do that, this first part's going to require the chain rule. And that would look like 1/2, well actually 1/4, because we already had a 1/2 sitting there. X squared plus 1 to the negative 1/2 times 2x because of the chain rule. When I look at this second thing, I'm going to treat that as 1/3 times 1 minus x, because it's much easier to take the derivative of. That way I don't have to do the quotient rule. The derivative of that then would be 1/3 times negative 1, which is basically negative 1/3. Like that. So I'm going to simplify this because I don't want to deal with it the way it looks. So let's see, I have a 2x on top and a 4 on the bottom, so that would give me an x on top and a 2 on the bottom. And then that negative 1/2 power is a square root on the bottom, like that. So now I'm going to set that equal to 0. I could find out where it's undefined, but the only place where it's undefined is actually an imaginary number when x squared is negative 1, so we're not going to worry about that. So when I go to solve this, I'd get a fraction on each side, cross multiply, I'd square both sides because I have a square root. I distribute that 4. I would subtract 4x squared from both sides, divide by 5, and then take the square root. So that's basically x is the square root of 4/5. I could simplify that, but I'm not interested in doing that right now. I should have a plus or minus, but again, the negative's not in the relevant domain, so I don't care about it. So when I go to do this sign line for total time prime, endpoints are 0 to 1. Square root of 4/5 is definitely between those. If I were to plug in something smaller than that into the derivative, I would end up getting something that's negative. And if I plugged in something on the right-hand side of that, I'd get something that's positive. So this decreases and increases. So there's a relative min there, basically. So since it's the only relative extremum, it is the absolute min. I don't need to compare it to the endpoints, anything like that. So I now have optimized it. I know that the minimum time happens when x is square root of 4/5, so I need to answer the question. And it says, what route will take the least amount of time? So there are several different ways you could answer this. What I would probably say is that I would want to swim to a point that is square root of 4/5 miles downstream and then walk the rest of the way to the camp. All right? So, example. There are 50 apple trees in an orchard. Each tree produces 800 apples. For each additional tree planted in the orchard, the output output per tree drops by 10 apples. How many trees should be added to the existing orchard in order to maximize the total output of the trees? Now, this one is an interesting problem because it's not really a diagram problem. It's more of a thought problem. So we're going to identify the quantity to be maximized or minimized. And again, maximize the total output of the tree. So we want the amount of fruit, basically, to be maximized. So let's call O. Do I want to do that? Because that is going to look a lot like a 0. So let's call Y the output of the trees. And then it talks about, the thing that affects that output is how many trees you plant in addition to the trees that you would already have in the orchard. So I'm going to let my dependent variable be the number of additional trees planted. Now what's interesting about this is if I started with 50 trees in the orchard, if I made the x a positive number, that would be like planting additional trees. If I made the x a negative number, that would be like taking negative trees taking trees out, which is a physically possible thing. So the x here is not going to be restricted to be 0 at its smallest. We'll revisit that in a moment. So write an equation for the quantity to be maximized. So the total output, which I'm calling y, is going to be, now if you think about this, this makes sense, just don't overthink it. The total output of the trees, the way you would count the fruit on the tree, is you would take the output per tree and you would multiply that by the number of trees. Now, that y, the dependent variable, depends upon two independent variables right now, output per tree and the number of trees. So we need to get this down into one variable. So if you look at the problem you get up here, it says you have 50 apple trees in an orchard, and then we are planting X additional trees. So if I wanted the total number of trees in there, it would be 50 plus X, keeping in mind again that X could be negative, meaning you're pulling trees up so the remaining trees can put more fruit out. And then you're told each tree produces 800 apples. For each additional tree planted in the orchard, the output per tree drops by 10 apples. So if we're talking about the output per tree, right now it would be 800. But for every tree we plant, which is X trees, we're going to be losing 10 apples of output. Let me write that a little more clearly. So it's 800 minus 10 times X. So that is the equation I'm trying to maximize. And if you notice, it's now one independent and one dependent variable. Now, I'm going to go ahead and FOIL this out. So let's see, that'd be 40 with 3 zeros after it. The benefit of making these videos without a calculator in my hand. Positive 800x and minus 500x will give me 300x. And then negative 10x squared. So that's the equation I'm going to actually optimize. And if I want to get the relevant domain, keep in mind again, this time it's physically possible to have negative trees. That means you're removing trees. But you can't, negative trees added. That means you're removing trees. But you can't have negative trees overall. So since my number of trees is 50 plus x, the smallest my x can be is negative 50. That would imply that I had removed all of the trees. Now, do I want that? No. But is it possible? Yes. Now, the way to find the upper end of this is to look at the other piece of this, which is the output per tree. If you let that go to 0, so like 800 minus 10x goes to 0, that means you planted so many trees that the trees are basically producing 0 fruit. And that would mark the most trees you could possibly plant. So if I took 800 minus 10x, set it equal to 0, solve for x, I would get 80. So my x is in between negative 50 and 80. So now I'm going to optimize this over that relevant domain. So I'm going to take the derivative. I'm going to find the critical points. I believe that's 15 in this case. I'm going to make my sign line. I forgot to put my prime. That was not good. I'm going to put my endpoints on it. I'm going to mark my critical point. I'm going to plug in numbers in the intervals into the derivative to see if it's positive or negative. If I plug in 0, it comes out positive. If I plug in like 30, it comes out negative. Increase, decrease. It's a relative max. It's the only relative extremum. Therefore, it is the absolute extremum. And this was asking how many trees should be added to the existing orchard. Well, that's what x was. So we're going to say we should add 15 additional trees.